Scott Miller of Newton's Forth in the UK, and today will be the first video in a series of tutorials covering many aspects of power measurement. Topics will address many of the common questions our application engineers receive. As I said, this is part of a series, so please look out for more videos in the future. But for today, what we're going to cover is initial turn on of a power analyzer, and also the importance of frequency synchronization for any AC power measurement. So let's take a look. At this time, the power analyzer is powered down and the AC supply to the test device is also disconnected. The universal breakout box in the top left corner of the video provides our means to conveniently break into the power line. The current flows out of the breakout box and through the shunt. The external current input on the analyzer samples a differential voltage measurement across the shunt via the red BNC lead. This is then converted into a current within the analyzer. Here we have the 4mm voltage connections and the external shunt BNC connection on the rear of the instrument. Notice we are not using the internal current shunt. As we know, the AC supply to the device under test is currently disconnected. We must be aware of this point as the only signal present under these circumstances is noise. As we turn the analyzer on, we will notice a very important point. The frequency fluctuates in the high kilohertz region. As previously mentioned, it is vitally important for accurate power analysis to be properly synchronized with the fundamental frequency. This is important as accurate phase angle measurement and harmonic analysis is reliant upon frequency synchronization of the measurement window. If we look at the voltage and current, we are only reading noise. The fundamental component in this case is the nominal 941 kHz. Let's take a look at the oscilloscope. As expected, we have only a small amount of noise present at the inputs. When power is applied to the test device and in turn the analyzer input, we would expect a voltage waveform to appear. If the inputs are configured correctly, we would expect the instrument to synchronize with the voltage waveform. So, let's connect the AC power source to the device under test and observe the 50 Hz 240 volt RMS waveform. Once the source is connected, the analyzer auto ranges to the 300 volt range. We do not expect to see a current waveform as by default the instrument is configured to monitor the internal current shunt. We will set the instrument up to monitor the external shunt later in the video. As expected, we see our sinusoidal voltage waveform. It is very important that we confirm the presence of a waveform. You can do this as we have here using the oscilloscope or alternatively in the RMS or power mode. If you use the power or RMS modes, this requires a little more confidence looking at digital data displays, but it's certainly a valid method. As we move to the power menu, you will see that the analyzer has synchronized with the 50 Hz waveform and is correctly reading the 240 volt RMS voltage signal. 50 Hz, 240 volt RMS. A common mistake is to attempt to synchronize the analyzer to a waveform that is not present, essentially synchronizing to noise. Let's see what we get if we attempt to configure the instrument so that it detects a frequency from the noise on the current input. Entering the acquisition menu, we can configure the instrument so that it will attempt to synchronize frequency to the current instead of the voltage. Using the cursors, we change the frequency reference to current. Of course, if a current waveform were present, this would be okay. This is purely for the purposes of demonstration, as we need to be confident how to diagnose unexpected results. Incorrect frequency reference is a common mistake. It is very obvious that if frequency reference is set to current, when there is no current waveform present, we have an erroneous frequency measurement. A sanity check indeed tells us there is no signal present on the current input. Rectifying this is simple and we simply reset the frequency reference to voltage. This reinstates the correct voltage and frequency measurements. What you may have noticed is we still haven't set up the current input to measure the current flowing through the external current shunt. We will quickly make the necessary changes in order to show a steady power reading before we finish this tutorial. Note that we are only using an external current shunt in order to demonstrate incorrect input configuration. The internal shunt can measure current values much lower than we are seeing today. Referring to the datasheet, the HF003 is the second shunt from the bottom, and we can see its resistance value is 470 milliohms. This is the value we will enter into the power analyzer. Let us remind ourselves of the waveforms being analyzed by the power analyzer. We have our sinusoidal mains voltage and the absence of our current waveform. This means we should look into the range menu and ensure that we are configured correctly for the external current measurement. If we scroll down to the current input and select external shunt, the measurement will now be taken from the BNC input. We then refer to the 470 mA shunt resistance value found in the datasheet and enter it into the shunt parameter. Pressing the home button takes us back to the oscilloscope screen, and we can see that we now have our standby current waveform. Returning to the power mode reveals the expected voltage, current and watts values, nominally 240 volt RMS, 50 milliamp RMS and 2.45 watts. If we enter the acquisition menu again, we can change our smoothing settings. Setting a slow time constant will stabilize the measured values further. It is important to remember that all N4L power analyzers perform gapless analysis. Therefore, even on a non-periodic waveform, stable results are quickly achieved. In the next tutorial, we will look further into the subject of frequency synchronization, where we explain the various coupling menus in the N4L power analyzers. Thank you for watching, and see you next time.